Today we're taking a look at section 4-3 on counting, and our learning outcomes. What we want to be able to do at the end of this section are: number 1, apply the fundamental counting principle to count a number of ways a multiple step task may be done. Number 2, use the factorial formula to count the number of ways that a group of n objects can be arranged. Number 3, apply the permutations formula to count the number of ways that R out of n objects can be arranged when all of the objects are different. Number 4, apply the permutations formula for identical items to count the number of ways that n objects can be arranged when some of the objects are identical. Number 5, apply the combinations formula to count the number of ways that groups of R objects can be selected from n objects. Number 6, select the appropriate counting method and solve any application problem involving counting. Number 7, use the TI 8384 plus to compute factorials, permutations, and combinations. So as you can see, we have a lot to accomplish in this particular section. Okay, one of my favorite counting methods is the fundamental counting principle or rule. Sometimes it's called a principle and sometimes it's called a rule. Both are the same thing. And what it says is when a task consists of two parts and the first part can be done in m ways, while the second part can be done in n ways, the number of ways to complete the task will be m times n. Now you can extend this if it's three parts, m times n times, let's say, p, 4 parts, m times n times p times r. You just keep multiplying. Depending on the number of tasks, you would have that number of factors in this particular formula. Okay, so I have some examples. Number 1, if you consider the problem of rolling 2 fair dice when one is red and the other is green, the red die has 6 possible outcomes and the green die also has 6 possible outcomes. So to figure out the total number of possible outcomes, we multiply 6 times 6 and get 36 possible outcomes when rolling both dice. And one of the things I like to do with dice, and let me see if I can get my pen working here. Whoops, I always do that. Alright, is if I'm saying a 1 on the red and a 1 on the green, a 1 on the red, a 2 on the green, a 1 on the red, a 3 on the green, and so forth. So I like to do them as ordered pairs. A 2 on the red and a 1 on the green, a 2 on the red, a 2 on the green, a 2 on the red, a 3 on the green, and so forth. So we can think of those as ordered pairs. And what you'll notice as you start making your table, and there is a table of this in the book, is that we have, for example, 2 ways to get a total of 3 on the 2 dice. One case is when the red is 2 and the green is 1, and the other one is when the red is 1 and the green is 2. So total number, 6 ways to get the red die, 6 ways to get the green die, 36 possible outcomes. Alright, example 2, we have a meal that consists of a salad where you have 2 choices, a meat where you have 3 choices, and a vegetable where you have 3 choices. With the fundamental counting principle, there will be 2 times 3 times 3, or 18 possibilities for ordering a meal. 18 different ways to order that particular meal. Alright, here's one for you to try. Suppose you have a student who has an early class. He's half asleep when he dresses, so he selected 6 shirts, 4 pairs of pants, and 8 pairs of socks, and 2 pairs of shoes that all go together. How many outfits are possible when he randomly selects a shirt, a pair of pants, a pair of socks, and a pair of shoes? And you're to use the fundamental counting principle to solve the problem. So pause this for a moment while you calculate your answer, and then we'll take a look at it in just a moment. hopefully now you have your answer to example 3. And so I've gotten my calculator out, and we have 6 times 4 times 8 times 2. So I'm coming up with 384 different outfits that he can put together. Okay, so we have 6 shirts, 4 pairs of pants, 8 pairs of socks, and 2 pairs of shoes. So 6 times 4 times 8 times 2 gives us 384. Hopefully you got that one correct. All right. Consider the problem involving selecting 3 officers from a club with 6 members. With the fundamental counting principle, we can see there are 6 choices for president. Since a person can't serve 2 offices, when we go to select the secretary, we only have 5 choices. And then when we choose a treasurer, we've removed 2 people, so we only have 4 choices. And so we come up with 120. Okay, so we have another example for you to try. Suppose a state decides to use 3 letters followed by 4 numbers to create a license plate ID numbers for the state. How many different plate numbers could be created using this particular setup? Use the fundamental counting principle to answer the question and assume that repetitions, and this is key in this one, repetitions are allowed. So pause the recording again and figure out your answer, and then we'll take a look at it. Okay, I'm assuming you've had a chance to come up with your answer. So we're working with 3 letters followed by 4 numbers. Okay, the letters, we have A through Z. There are 26 of them. Since there are repetitions are allowed, then for the second letter we can have 26 choices, and the same thing for the third. Now the numbers have to be 0 through 9, so we have 10 choices for that. And again, repetitions are allowed, so we have 10 choices. So we're assuming that a 0 could occur as the first number there. Some cases they'll tell you 0 can't start it. Okay, so we have 26 raised to the third times 10 raised to the fourth, and that gives us 17576 followed by 4 zeros. Get the commas in here so I can read it. 175,760,000 different possible IDs for those cars. Okay, so the fundamental counting principle. And one of the things I wanted to point out is that any problems where you're doing counting and repetitions are allowed, you have to use the fundamental counting principle. That's actually the only one that will work in that particular case. So I just wanted to give you a heads up on that. All right, now we move on to the factorial formula. And in order to apply the factorial formula, we have to understand what a factorial is. And so I've tried to define what it is. A factorial expression is indicated by an exclamation mark. And so what happens is we multiply all of the whole numbers, actually all of the natural numbers, from that particular number that's indicated in front of the exclamation mark all the way down to 1. So 2 factorial is 2 times 1. 3 factorial, we have all the factors, the natural numbers, down to 1. 4 factorial, we multiply from 4, 3, 2, 1. 5 factorial, we start 5 and work all the way down to 1. 10 factorial, we would start at 10 and work all the way down to 1. So that's what we mean by factorial. We do have a special definition. 0 factorial is defined to be 1. 0 factorial is defined to be 1. So that's just simply a matter of remembering that. Now, most calculators do have a factorial button. On the TI-83 or 84 Plus, what you will be doing, and let's just do one of the numbers that I have up here. Let's do 5 factorial. What you do is you enter the 5, then you go to Math, and PRB. You want to use the arrow keys to go across to PRB. And number 4 is factorial. And then you press enter, and you can see we're getting the 120. And we'll do it again for 10. So you want to enter the 10, go to Math, work across to the PRB, and we want 4 is factorial, and then press enter. And you can see we get 3,628,800. Okay, and we'll do, actually I'll do a couple with the calculator when we get to some practice problems a little bit later. Okay, the factorial rule, which is based on the factorial formula, says that if you're arranging all n of n objects, the number of arrangements of those objects will be n factorial. So, example 1, suppose you have 7 books and there is space on your shelf for all 7 of the books. How many different ways can you arrange the 7 books? Well, since we're arranging all 7 of 7, the factorial rule says there are 7 factorial ways to arrange the books. So you can use your calculator if you want, or you can multiply it out, 7 times 6 times 5 times 4 times 3 times 2 times 1, and you get 5,040 ways. All right, let's take a look at example 2. This is one for you to try. Suppose that 12 friends go to the movie theater and find 12 seats in a row where they can all sit. How many ways could the 12 friends be arranged in those 12 seats? Use the factorial rule to find your answer. So pause this for a moment and see if you can come up with the answer. Okay, I'm assuming you have the answer here. We have 12 friends and 12 seats, so we're using all 12 of them. So according to the factorial rule, we'll have 12 factorial ways to arrange them. And going to my calculator, 12 factorial, oh, it's a big number, 479001600. So let me, 479,000,001,600. 479,000,001,600. Okay, I think I'm about out of time on this particular recording, so I'll pick up with permutations on a separate recording.